In this video, we are going to find out the shear stress profile for the given cross section, and also we are required to find out the location of neutral axis with respect to the top of the flange. We are given with a shear force of 60 kilonewtons. The cross section is a T-shaped cross section. The flange is of width 200 millimeters. The thickness of flange is 40 millimeters, and whereas for the web has a depth of 100 millimeters and a thickness of 20 millimeters. First of all, for locating the centroid or the neutral axis, we need to find the centroid of the cross section. For solving the first part of the question, that is, show the neutral axis is 34 millimeters from the top of the flange. Starting with the first part, we need to locate the centroid. Let's call this shape as number 1, this as shape number 2. For finding out the centroid, note that in previous videos we have discussed in detail for calculation of centroid. For shape number 1, the area is 200 by 40. So that comes out to be 8,000 millimeters square. For second shape, the area is 100 multiplied by 20. That comes out to be 2,000 millimeters square. The sum is 10,000 millimeters square. The y distance, let's consider the top as a reference since we are required to find out the location of neutral axis from the top fiber. So considering top as the reference, for the shape number 1, the centroid is 20 millimeters. Since it is a rectangle, so the centroid is as half of the height. For shape 1, it is 20 millimeters. For shape 2, we move past the 40 millimeter plus the half of this rectangle, that is 50. The sum gives us 90 millimeters. The product of A dot Y is 160,000. The product of A dot Y here is 180,000. Let's add these values. We get 3, 4. As in previous videos, we discussed for calculation of centroid, we know that centroid is substituting the values. Know that it was in millimeters. That comes out to be 34 millimeters. Hence, we have proved that the centroid from the top flange is 34 millimeters. Centroid or neutral axis here, it is same. For the next part, we need to plot the shear stress profile. This is the answer for part number 1. Let's call this part 1, this is part 2. Answer number 1. For part number 2, we need to find out the shear stress profile. The formula for shear stress profile is, we're starting with part 2 solution. The moment of inertia remains constant for a cross section. The shear force remains constant for a cross section, that is given as 60 kilonewtons. What we need to find out by varying the location of the fibers is Q and T, where T is the thickness and Q is the first moment of area. Please refer to the previous video in which I have discussed the details of the variables involved in the formula. The equation is 60,000 Newton multiplied by Q divided by moment of inertia into T. Let's call this as equation number 1. The next part, we have to find out the moment of inertia. Considering the same figure for calculation of moment of inertia, using parallel axis theorem and discussed in previous examples, the moment of inertia of shape number 1, since the load is applying in this direction, so we use base as the perpendicular dimension. So it comes out to be 200 into 40 cube divided by 12. There is 106 exponent 4. For the next shape, that is shape number 2, the base is 20 millimeter and the height is 100. It comes out to be 1666.6.7. The area is 8,000. The area for shape 2 is 2,000. Now the dy part is the interesting part. For shape number 1, the dy is the distance of shape 1's own centroid to the whole body centroid. Let's consider the figure here I'm drawing. This was shape number 1. Okay. So the centroid of shape number 1 should be located at half of this 40 millimeter, that is 20 millimeters, and the whole body centroid is located at 34 millimeters. So the distance between 20 millimeter and 34 millimeter is 34 minus 20, that is 14 millimeters. Now for calculation of dy for shape number 2, we have to find out the distance of this shape's centroid to the whole body centroid. Note that this distance is 40 and this distance is 50. So the total is 90 millimeters. And the centroid of the whole body was 34. So 90 minus 34 is equals to 56 millimeters. Note that you can also put minus sign or plus sign here, but that doesn't matter because in the end, even if it is a minus sign, the square will make it a positive value. So the product of a dy square makes and the product of a dy square makes it 627. Sum of a dy square comes out to be 784, while the sum of ix comes out to be 27333.4. So Substituting these values in the formula for calculating the whole body centroid is we get a value of 10573333.4 millimeter 4. That is the moment of inertia of the whole body. Now I need to find out the shear stresses for the different fiber locations in the cross section. Let's name the different fibers of the cross section. Let's call this as fiber A. The fiber at 34 millimeter as the neutral axis. Note that there would be a neutral axis above the fiber, that is neutral axis 1, and neutral axis part below the fiber. So we will get two stress values. But keep in mind that there is only single neutral axis line, but the stress values will be 2. It depends that the stress values may be similar or have a different magnitude. But right now we need to consider in general form that at neutral axis there are two stress values, one due to the area above neutral axis and two due to area below the neutral axis. So we will find out both of the values in order to plot the shear stress profile. Let's call this fiber as fiber B. The fiber B will have two stress values, one due to thickness 200 millimeters and two due to thickness 20 millimeters. Note that the NA subscript denotes the neutral axis. One due to thickness 200, one due to thickness 20 millimeter. So starting with the fiber AA. So AA is equals to 60,000 Newton. The equation A is used in each fiber stress calculation. Moment of inertia was 10573333.4 into the thickness at fiber A is 200 millimeters. First we will find out the Q. Let's call this equation number 2. So the QAA value is area AA into the lever arm of AA from the whole body center. The area AA, since it is just a line, the fiber is just a line, there is no area exists at point or fiber AA. So it is 0. Into the distance YY, anything multiplied by 0 comes out to be 0. So equation number 2 implies that shear stress at fiber AA is 0. Now, in the next step, finding out shear stress at fiber neutral axis. So, at neutral axis 1 due to area above the neutral axis is equals to 60,000, that is the applied force, into QNA1 divided by 1057 that is the moment of inertia, which is always constant for a cross section, into thickness. The thickness at fiber Na is 200. Let's call this as equation number 3. QNA is equals to the product of area into lever arm. The area above neutral axis, that is this one area, is 200 multiplied by 34. That is the depth of neutral axis from the extreme top fiber. Now the YA part is interesting. The shaded area's centroid distance to the whole body centroid, which will be simply rectangular centroid, as it would be 34 divided by 2. That comes out to be 115,600 millimeter cube. So substituting the value of QNA into equation number 3, we get a value of tau Na1 as 3.28 Newton per millimeter square. At neutral axis above, due to above the area, the shear stress. Now we will use the same procedure, but the difference will be we will use the area below the neutral axis and the centroidal distance below the neutral axis. Considering the area below the neutral axis, the total area will be the shaded one, as now we are considering the area below the neutral axis. Let's name this as tau Na2 is equals to 60,000. That was the applied force, which is constant for a cross section. QNA2 multiplied by the moment of inertia, which is also constant for a cross section, into the thickness. The thickness at the considered fiber is 200. Only unknown is Q. QNA2 is the product of area Na2 multiplied by the lever arm. The area is, since the thickness of this part is 40 millimeters and the neutral axis was at 34 millimeters. The thickness of this part is 6 millimeters. Since 34 minus 40 millimeter remains with 6 millimeter. So the area part is 6 into 200 plus this part. The 100 millimeter into 20 millimeter. Into the product. We will find out the centroid directly, as we previously discussed in the videos. Centroid is summation of A dot Y divided by summation of area. The centroid will directly be found out by, for this area the centroid will be 6 into 200 100, that is the area, multiplied by 6 divided by 2, that is the half of distance due to it being a rectangle, plus the area 100 into 20 multiplied by the distance 6 mm plus to the centroid of this rectangle, that is 100 divided by 2, since it is a rectangle, divided by simply the summation of area below the neutral axis. So the value comes out to be 36.125 millimeter. Substituting the value of 36.125 millimeter in equation number 4, we will get a value of shear stress below due to below the area of neutral axis as 3.28 Newton per millimeter square. Note that in the previous page we calculated the shear stress due to area above the neutral axis. The value was same as 3.28 millimeter Newton per millimeter square. It is a certain case that the shear stress due to area above the neutral axis and shear stress due to area below the neutral axis have similar magnitude. It's only case in some time, not always. Now we will be finding out the stress at the junction of the two rectangles. We named the rectangle fiber at the junction as BB. So for BB, there will be two stresses. One due to the thickness T is equal to 200 mm and two due to thickness 20 mm. So we will devise a general formula for BB1 due to thickness 200 mm. The tau BB1 is equals to 60,000, that is the force constant for a cross section here, moment of inertia, multiplied by QBB1 multiplied by the thickness, that is 200. Let's call this equation number 5. For QBB1, we need area BB1 multiplied by lever arm. Drawing a rough sketch just to show you where the fiber BB was located. BB1 is due to thickness 200. Okay, so the neutral axis was at 34 millimeter and the fiber BB is at 40 millimeter. For the distance y, since we are considering the shaded area, the distance will be from centroidal axis to the centroid of the area below neutral axis, that is 50 millimeter. So this will be 50 plus 6 millimeter, the distance from centroid of whole body to the shape centroid under consideration, and the area will be simply area below fiber B is simply 100 multiplied by 20 millimeters. The QBB1 comes out to be 1120. So putting this value in this equation, equation 5 gives us a value of tau B1 as 3.18 Newton per millimeter square at this fiber due to thickness 200. Now we'll repeat the procedure for fiber BB by using thickness as 20 millimeter. For fiber BB2, that is due to thickness 20 millimeters. The values will remain the same. QBB2 will be same as QBB1 because the area is same and the centroidal distance will also be 56 millimeter. That remains the same. The only thing that would be different is the thickness. So the value comes out to be 31.7 Newton per millimeter square. Since the area reduced, the stress drastically increased. The stress is inversely proportional to the area variable. As we have noticed, the thickness decreased, the stress drastically increased. So that was tau BB2. Now, finding out at the last, let's call this point S fiber as CC. Area CC into the lever arm CC. The area CC is 0, hence QCC is equals to 0. And if we substitute the value in VQ over IT, the whole value comes out to be 0. Hence tau CC is 0. Now make a table of values, that is tau and the fiber. This is the last step required in plotting the shear stress profile. This was the fiber AA, this was neutral axis, this was fiber BB, this was fiber CC. Fiber AA, neutral axis due to area above, neutral axis due to area below. Fiber BB due to thickness 200, fiber BB due to thickness 20, and finally fiber CC. The stress values which we found out were 0 and 0 at fiber CC and fiber AA. At fiber NA above the neutral axis, it was 3.28 Newton per millimeter square, and surprisingly, due to area below the neutral axis, the value was same. It is no hard and fast rule. It may be different or it may be same. Fiber BB1, the value was 3.18, and fiber BB2, it was increased drastically due to reduction in thickness, since stress is inversely proportional to the area. The more the area, the less the stress will the member take. So plotting these values will yield the results as 0, 0. At AA it is at neutral axis, it is 3.28. Above and below are same. It is a second degree curve or parabola. Below neutral axis same. Fiber BB, the value reduces 3.18. And fiber BB2, the value increases due to reduction in thickness 1.7. And fiber CC, the value is 0. Joining them by a second degree curve. This is the stress profile required. Thank you for watching. In further videos, we will discuss about the torsion and the shear stresses developed by the torsion and the angle of rotation. Please subscribe for more.